I'm Mr. H and I'm welcoming you all to this video where we are looking at three organic compound alcohols. Which one is the strongest acid? You have compounds A, B, and C. When we're looking here at compound A, you know CH3CH2OH is ethanol. We can write it out. It's ethanol. When you look over here, you have 1, 2, 3, and you'll number it in this way. The hydroxyl carbon is precedent over the alkene. Now what will you call this? Well, you have the alcohol and the alkene on the same carbon. You can say this is a 1-propan, and this En indicates as an alkene, and then Ol for your alcohol. Here you know clearly we have a phenol, a hydroxyl group attached to your benzene. Which of these three is the strongest acid? Generally, alcohols are not acids, but from a relative point of view, with regards to organic acids, these are truly acids. But which one is the strongest? Your representative reaction is this. You're looking here at an alcohol where the R represents the rest of the molecule. What is the likelihood it will undergo this reaction to generate a proton and a oxide? And your oxide will be looking at this, and we'll call this an alkyl oxide. Or you can say, in other words, an oxide. These are your anions, and we'll give it a negative charge. Alkyl oxide or an oxide. You're looking here at the strength of this or the stability of that to make your judgment over here. The likelihood that the reaction will proceed in this direction towards the right and generate these will give an indication of the acidity. If your reaction is preferring to go in this direction to go back to the alcohol, then you know you're looking at something very, very weakly acid. So this right here is a representative reaction, and one by one, A, B, and C, let's go through these compounds. When I'm looking here at A, which is my ethanol, you know the reaction will be like this. CH3, CH2, I have this 2 electrons and I have a hydrogen. The 2 electrons of this bond will go back to the oxygen, the hydrogen will go away to generate your proton, and you'll generate your ethoxide anion, which you know to be now like this. And here's your anion, and we'll call this ethoxide anion. Proton has been developed. The 4 electrons on the oxygen are now 6 because 2 from this bond have gone to oxygen. What is the stability of the ethoxide anion? You have such a large heavy density here, charge density. Oxygen is bearing so much charge. Then you have these alkyl groups that are donating charge because they like to transmit charge away. Now you're having an area of even further charge density, making this relatively unstable. You have so much charge on that oxygen, it's unstable. Given the fact that ethoxide anion is a very strong base, it's going to look back for this proton and reattach it to regenerate the alcohol. You have 2 things going on over here. You have a very strong base which wants to reattach the proton and go back to the alcohol, and you have a oxygen which is heavily charged excess. So much charge on this oxygen makes it unstable. The reaction here is towards the alcohol, hence this right here is a very weak acid, if at all even an acid. You can cross it out because it's certainly not the strongest from the 3. Look right here at compound number 2, or B, we'll call it B, 1-propanol. When you're looking at this, you have this CH3, you have CH double bond, CH, the double bond here, and your hydroxyl right over here. The 2 electrons from the oxygen-hydrogen bond will be plucked away, go into oxygen, the hydrogen will drift away as your proton. What you will be left with here is an oxide, but we'll name it properly. You have this. You're going to have this right here. We can call this 1-propanoxide, and that's what, nothing wrong with calling that 1-propanoxide anion. That negative charge is an anion. We have a negative charge over here, obviously. 1-propanoxide. What is the stability of that propanoxide? Well, again, you have an oxygen with a very high charge density. It's very high. But can we use that double bond to our benefit? We can, by means of resonance. There's a resonance structure available over here which stabilizes that negative charge, and it makes this anion stable and favorable. Hence you can see the reaction proceed in this direction and generate more of these. So it can be considered an acid, an organic acid. But what is that resonance structure? You will basically form a double bond over here, and then you will shuffle electrons, and I'll show you the resulting structure. It will look like this. You have CH3, nothing's going to happen with this. But here you will have your negative charge come over here. You have a net negative charge of 1. Here you must have a negative charge of 1. You should maintain charge balance. You're going to develop what will look like this. A double bond between the oxygen And now that right there is your resonance structure, and you can show it like this. Here's your one resonance structure with a negative charge, the negative on oxygen. Here's your other resonance structure with a negative charge on this carbon number 2. But it is exactly what it is. And you have a rather charge stabilization order. The oxygen is bearing the excess charge here, now carbon is bearing the excess charge, but you can shuffle between these two and give that structure relative stability. Hence you can say it's relatively stable or favorable, and you can say that this to be an acid, not a very strong acid, but it can behave as an acid and you can generate some protons. So we've shown you this and it should be good. It certainly will not be the strongest. What will be the strongest will be phenol, and I will tell you why. A reason being upfront, because here I have only one resonance structure. When you look at phenol, you'll have multiple resonance structures. The more resonance structures you have, the more you can stabilize the oxide, your anion, and the more favorable it is, the more likely you'll develop the protons. So let's look at compound number C. When you are looking at phenol, you have something which looks like this. Here it is, your electrons, and you have your benzene ring. This is what it looks like. The electrons from this bond are going to go back to the oxygen, the proton will drift away. When you're looking at it, you'll obviously have your proton here. I'm not going to show it to you anymore. I'm removing it and I'm putting it right over here. We've developed a proton. Now I'm going to show you this anion, which looks something like this. And this is what it is. What is this called? It's called phenoxide anion. Phenoxide anion. It's relatively stable because you can shuffle this around resonance structures. What are some of your resonance structures? You can send this over here and you can shuffle things around. When you shuffle it around, you look at a double bond forming over here between the oxygen and this carbon, and it looks something like this. When you do that, now you're looking here at a negative charge over here. Everything else is still as is. Then you can shuffle this around some more. When you shuffle it around some more, you can transmit this over here, you can transmit over here, and you look at and get another structure which develops, and it looks something like this with a negative charge coming down here. You have a double bond here, double bond here, you have that and that. You can do yet another over here, and you can imagine what the other one will be. It'll be the mirror image of this. What I can do for showing it to you is I can bring it over here. This negative charge will come over here and this will come right over here. When you do it, you have a structure which develops and it looks something like this. You have a double bond over here, now you have a double bond over here, and you have your negative over here. You obviously have that, and we'll close out the resonance structures. I have 1, 2, 3, 4 resonance structures. The 4 resonance structures gives you added stability of this phenoxide anion. It makes the reaction favorable here towards the right. Hence, when you look at all of these, the strongest acid is C, followed by B, followed by A. This right here is the strongest acid because it has the most resonance structures. This is the next strongest acid because it has at least one resonance structure. This is the weakest, or not even an acid, because it has no resonance structures. A very strong base which wants to go back to generating the alcohol. With that, we bring this video to an end. Thank you for watching.